8 Fig 8.1 shows parallel wave fronts of a light wave in ice. The wave fronts are incident on a boundary with air. The speed of the light wave in air is 3.0 times 108 m/s. The refractive index of the ice is 1.3. A. On Fig 8.1. I. Draw the wave fronts of the wave that passes into the air. Wave fronts in the air. Parallel to each other. Make a larger angle with the boundary than wave fronts in ice and from top left to bottom right. At least one wave front meets a wave front in ice at the boundary. 2. Draw arrows to show the direction of travel of the refracted wave. Arrows at right angles to wave fronts pointing away from boundary. 3. Label the angle of incidence I and the angle of refraction R. Acute angle between any wave front in ice and boundary marked I. Acute angle between any wave front in air and boundary marked R. Or. In ice, normal at boundary and ray perpendicular to any wave front both drawn. Angle between normal and ray in ice marked I. In air, normal at boundary and ray perpendicular to any wave front both drawn. Angle between normal and ray in air marked R. B. Calculate the speed of the light wave in the ice. N equals speed in air / speed in ice, or N equals var / vice, or vice equals var / N. Or 3.0 times 108 / 1.3. 2.3 times 108 m/s. 6. A. Fig 6.1 shows crests of a water wave moving from left to right in a harbor. I. On Fig 6.1, draw 3 more crests to the right of point A. 3 straight crests, to the right of a parallel to incident crests and same lambda by I. Curving round correct way below A. 2. State the name of the wave process that occurs as the wave passes point A. Diffraction. B. Fig 6.2 shows the crests of another wave moving from left to right in a different part of the harbor. This wave moves from deep water to shallow water. I. On Fig 6.2, draw an arrow to show the direction of movement of the wave after it has passed into the shallow water. Correct arrow perpendicular to wave fronts. 2. State the name of the process that occurs as the wave passes into the shallow water. Refraction. 3. Complete Table 6.1 to state whether each of the properties of the wave increases, decreases, or stays the same as the wave passes into the shallow water. Wavelength, decreases. Frequency, stays same. Speed of wave, decreases. 7. A. Fig 7.1 shows a converging lens and the image I formed when an object is placed to the left of the lens. The principal focuses are labeled A and B and the center of the lens is labeled C. I. On Fig 7.1, draw 2 rays to locate the position of the object. Draw the object and label it O. 1 correct ray. 2nd correct ray. Rays intersect above axis to left of A and object drawn from axis to intersection. 2. Ring all of the following distances that are equal to the focal length of the lens. Of AC CB to of AC CB. B. Fig 7.2 shows green light passing through a triangular glass block. Red light enters the triangular glass block shown in Fig 7.2 along the same path as the green light. I. On Fig 7.2, draw the path of the red light within the triangular glass block. Ray and prism refracted down less than green ray. Fig 7.3 shows green light passing through a rectangular glass block. Red light enters the rectangular glass block shown in Fig 7.3 along the same path as the green light. 2. Draw the path of the red light within the rectangular glass block. Ray in rectangular block refracted down less than green ray. 3. Draw the path of the red light after leaving the rectangular glass block. Ray leaving rectangular block parallel to incident ray. 5. A. State the name of the reflection of a sound wave or ultrasound wave. Dash. Echo. B. Fig 5.1 shows an ultrasound wave being used to scan an internal organ of a human body. The ultrasound wave has a frequency of 2.0 MHz and passes through human tissue at a speed of 1500 m/s. Calculate the wavelength of the ultrasound wave in human tissue. Lambda equals 7.5 times 10 to 4 m, or lambda equals v/f, or v equals f lambda in any form. Lambda equals 1.5 times 103/2 times 106. C. Fig 5.2 shows crests of a wave from a point source S approaching a straight barrier. I. On Fig 5.2, indicate and label one wavelength. Labeled wavelength of incident wave. On Fig 5.2, draw three crests of the wave reflected from the barrier. 3. Part circles to the left of the barrier and centered to right of the barrier. Wavelengths of reflected and incident waves same. 6. A. Fig 6.1 is a full-scale diagram showing a converging lens, the two principal focuses f1 and f2 and an object PO. On Fig 6.1, draw two rays from point O of the object to determine the position of the image. Label the image IJ. Measure the length of the image. Image length equals ... Any two correct rays from O through optical center and beyond. From O parallel to principal axis to center line of lens, then through f1. From f2 through O to central line of lens, then parallel to principal axis. Rays traced back to intersect and 2.4 to 3.6 centimeters. B. Ring 3 descriptions of the image. Diminished, magnified, real, same size same way up as object, upside down compared to object, virtual. Magnified. Same way up as object. Virtual. C. Fig 6.2 shows three rays of green light passing through glass blocks. Three rays of red light approach the glass blocks on the same paths as the rays of green light. On Fig 6.2, draw the paths of these rays of red light to the right of the glass blocks. One ray from each prism refracted towards principal axis. Rays converge to the right of original convergence on the principal axis. 5a. Boy looks at the image of a clock in a plane mirror. Fig 5.1 shows the mirror, the clock, and the position of one of the boy's eyes. A. I. On Fig 5.1, draw a ray of light from the clock, reflected to the boy's eye. Straight line from clock to mirror and from mirror to eye with correct arrows. Angle of incidence equals angle of reflection. 2. On Fig 5.1, mark with an X the position of the image of the clock. Correct position of image. 3. State whether the image formed by the mirror is virtual or real. Explain your answer. Virtual, no mark. And cannot be projected on a screen / light doesn't pass through image. 4. Fig 5.2 shows the image of the clock seen by the boy. The boy now looks directly at the clock. On Fig 5.3, draw what the boy sees. B. I. The clock is illuminated by a source of monochromatic green light. State the meaning of monochromatic. Monochromatic light is light of a single frequency. 2. The green light has a wavelength of 5.6 times 10 to 7 m. Calculate the frequency of this green light. 5.4 times 1014 Hz, or speed of light equals 3 times 108 m/s. F equals v/lambda in any form, or 3.0 times 108/5.6 times 10 to 7. 5. A. Fig 5.1 shows a semicircular transparent plastic block. A ray of light is incident normally on the curved surface of the block. The refractive index of the plastic is 1.5. I. Calculate the critical angle for the plastic. 42 degrees north equals 1/sin C, or C equals sin 1/n, or C equals sin 1/1/1.5. 2. On Fig 5.1, draw the path of the ray in the block and after the ray emerges from the block. Ray continues along radius of semicircle within plastic. Ray reflected inside plastic on straight edge, with angle of reflection equals angle of incidence and emerges from block along the normal. B. Fig 5.2 is a full-scale diagram of a lens and an object O. The point marked F shows the position of a principal focus of the lens. I. Determine the focal length of the lens. Focal length equals 7.2 centimeters. 2. On Fig 5.2, draw two rays from the object to locate the image. Label the image I. 2 correct rays from. Ray from top of object through center of lens. Ray from top of object that would pass through F on LHS of lens refracted parallel to the principal axis. Ray from top of object to lens, parallel to principal axis, refracted through F same distance on right of lens as F marked on left of lens. 2 rays correctly extended back to intersect to left of object and line from principal axis to top of image labeled I. C. Fig 5.3 shows a simplified diagram of an eye with rays from a distant object and the path of the rays inside the eye of a person with short sight. On Fig 5.4, draw an additional lens outside the eye to correct short-sightedness and show the path of the rays inside the eye. Diverging lens in front of eye lens. Rays meeting on the retina. 6. A. Sound waves have compressions and rarefactions. Explain what is meant by compression and rarefaction. Region where particles are closer together than normal or region where there is a greater pressure than normal. Region where particles are further/far apart than normal or region where there is a lower pressure than normal. B. We can see light from the sun but we cannot hear any sound from it. State the reason for this. Light does not need a medium to travel through. Sound needs a medium to travel through and there is no medium between sun and earth. C. During a thunderstorm, an observer sees the lightning almost immediately but hears the sound of the thunder several seconds later. The thunder and lightning are produced at the same time. The sound of the thunder is heard 9.0 s after the lightning is seen. The speed of sound in air is 340 m/s. Calculate the distance from the thunderstorm to the observer. 3100 m or 3.1 kilometers. V equals S/T or S equals VT or 349. D. In a lightning strike, there is a current of 3.0 times 104 A for 48 milliseconds. Calculate the charge that flows. 1400 C. Or I equals Q/T or Q equals IT or 3.0 104 48 10 to 3. T equals 48 10 to 3 or T equals 4.8 10 to 2 or T equals 0.048 scene. 0625_S19_MS_41.pdf. 6. Green light of frequency 5.7 times 1014 Hz is traveling in air at a speed of 3.0 times 108 m/s. The light is incident on the surface of a transparent solid. Fig 6.1 shows the wave fronts and the direction of travel of the light in the air. The light travels more slowly in the transparent solid. A. Explain, in terms of the wave fronts, why the light changes direction as it enters the solid. You may draw on Fig 6.1 as part of your answer. Idea of one side of wave front enters/hits solid first or wave front does not all hit the solid all at once. Idea of the side slowed down first or the side delayed relative to other side. Angle of wave front changes or different parts of wave front delayed by different amounts. B. The refractive index of the transparent solid is 1.3. I. The light is incident on the surface of the solid at an angle of incidence of 67 degrees. Calculate the angle of refraction of the light in the solid. N equals sin. Sin in any form or N1 sin. Theta 1 equals N2 sin. Theta 2 or 1.3 equals sin 67 degree sin r. Or R equals sin 1 sin 67 degree/1.3 or sin 10.71. 45 degrees. 2. Determine the wavelength of the green light in the transparent solid. VTS equals C/N in any form or VTS equals C slash N or 3.0 times 108 slash 1.3. 2.3 times 108 or 3.0 times 108 slash 1.3. Lambda equals V slash F in any form or lambda equals V slash F or 2.3 times 108 slash 5.7 times 1014. Or 3.0 times 108 slash 1.3 times 5.7 times 1014. 4.0 times 10 to 7 m. Or alternative approach. Lambda equals V slash F in any form or lambda equals V slash F or 3.0 times 108 slash 5.7 times 1014. 5.3 times 10 to 7 or 3.0 times 108 slash 5.7 times 1014. Lambda G equals lambda A slash N in any form or lambda G equals lambda A slash N or 5.3 times 10 to 7 slash 1.3. Or 3.0 times 108 slash 1.3 times 5.7 times 1014. 4.0 times 10 to 7 m 0625 underscore S19 underscore MS underscore 42.pdf. 6. A. Fig 6.1 shows a water wave in a ripple tank. I. State the name of the process that occurs as the wave moves from region A to region B. Refraction. 2. Suggest a cause for the change in direction of the wave. Waves move faster in region B or slower in region A. B. Fig 6.2 shows a transverse wave. On Fig 6.2, draw a wave which has half the amplitude and a greater frequency than the wave shown. At least one complete cycle with half the amplitude. At least one complete cycle shorter time period. C. A train travels along steel rails. A person waiting at a station hears the sound of the train through the rails before he hears the sound through the air. I. Explain why this happens. Sound travels faster in steel slash metal slash solid slash the rail than in air. 2. The speed of sound in the rails is 5800 m/s. Calculate the wavelength of sound of frequency 1100 Hz traveling at this speed. V equals F lambda in any form or lambda equals V slash F. Or lambda equals 5800/1100. Lambda equals 5.3 m. 7. A. In Fig 7.1, a converging lens projects a sharp image of an object O onto a screen. Complete the paths of the two rays from the object to the screen. Both rays straight to left of lens and top ray bends clockwise and bottom ray bends anti-clockwise. Both rays converge to meet on the central line at the screen. B. The converging lens in A is replaced with a thinner converging lens. The object O and the screen remain in the same positions as in A. The thinner converging lens has a longer focal length than the converging lens in A. Complete the paths of the two rays from the object to the screen in Fig 7.2. Both rays straight to left of lens and top ray bends clockwise. Less than in A and bottom ray bends anti-clockwise less than in A. Both rays converge and slash would meet beyond screen. C. A converging lens is used as a magnifying glass. The focal length of the lens is 10 cm. I. Describe the position of the object in relation to the lens. Object closer to lens than 1 focal length. 2. Describe the position of the image in relation to the lens and the object. Image same side of lens as object. Or image further from lens than object. 3. Give 3 properties of the image formed by a magnifying glass. 1 from 3 of, image enlarged slash magnified, upright slash goes up, virtual. All 3, image enlarged, upright, virtual. 0625 S19 MS 43.pdf. 6. A. Fig 6.1 shows wave fronts of a wave approaching a narrow gap and passing through the gap. The wavelength is lambda. I. State the name of the process that occurs as the wave passes through the gap. Diffraction. 2. A wave with a wavelength lambda/2 approaches the same gap. On Fig 6.2, draw 3 wave fronts for this wave as it approaches the gap and 3 more wave fronts as the wave continues beyond it. Wave on left half the wavelength of waves in Fig 6.1. Both wavelengths on right same wavelength as on left. Much less spreading than in Fig 6.1. B. Table 6.1 shows 5 different types of electromagnetic wave. In the blank column in Table 6.1, write the numbers 1 to 5 to show the order of wavelength. Write 1 for the wave with the shortest wavelength and 5 for the wave with the longest wavelength. 3 numbers correct. All 5 numbers correct. Correct answer, 1, 4, 5, 3, 2. C. I. State the speed of radio waves in air. 3.0 times 108 m/s. 2. A radio station transmits radio waves with a frequency of 96 MHz. Calculate the wavelength of these radio waves. V equals F lambda in any form or lambda equals R. V/F. 96 times 116. Lambda equals 86. 3.010. 96 10 times equals 3.1 m. 7 Fig 7.1 shows light approaching a boundary between two materials at speed v. The speed of the light after crossing the boundary is 1.3 v. A. Determine the angle of incidence. 40 degrees. B. Calculate the angle of refraction. N equals 1.3 or seen in calculation. Sin I/sin R equals N in any form or sin 40/sin R equals N sin I/sin R equals 1/N. Sin R equals 1.3 times sin 40 degrees R equals 57 degrees. 0625_S20_MS_41.pdf. 5. The distance between the center of a thin converging lens and each principal focus is 5.0 centimeters. A. Describe what is meant by the term principal focus for a thin converging lens. Point where incident parallel rays meet after passing through lens or origin of rays that emerge parallel after passing through lens on principal axis or use of term paraxial or center line. B. The lens is used as a magnifying glass to produce an image I of an object O. I. Underline the terms that describe the nature of the image produced by a magnifying glass. 2. Diminished, enlarged inverted real same size upright, virtual. Enlarged virtual upright. 2 correct answers underlined. And no more than 1 wrong answer underlined. 3 correct answers underlined. And no wrong answer underlined. 2. Fig 5.1 is a full-scale diagram of the lens and the image I. 1. On Fig 5.1, mark both principal focuses and label each of them F. 1. Both principal focuses marked at points 5.0 cm from the optical center. 2. By drawing on Fig 5.1, find the position of object O and add object O to the diagram. Any two construction lines from line from top of eye towards far principal focus and traced back from lens horizontally. Line from top of eye to and through center of lens. Horizontal line from top of eye to lens and traced back to near principal focus O marked with top at intersection. 3. Using Fig 5.1, determine the distance of object O from the center of the lens. 2.7 cm distance 3.1 cm. 6. The speed of sound in air is 340 m/s. A. Calculate the range of wavelengths for sounds that are audible by a healthy human ear. Lambda equals V/F or 340/20 or 340/20. 0.017 m. And 17 m. B. Sound waves are longitudinal waves. Describe how a longitudinal wave differs from a transverse wave. Longitudinal wave vibration direction parallel to propagation/energy travel direction. Transverse wave vibration direction perpendicular to propagation/energy travel direction. Consists of rarefactions and compressions. 0625_S20_MS_42.pdf 5 Fig 5.1 shows crests of a wave approaching a barrier where the wave is reflected. A. On Fig 5.1, draw 3 crests of the reflected wave. 3 wave fronts parallel to each other and same angles of reflection and incidence both by I. 2 wavelength same as original wavelength by I. 3 reflected waves meet incident waves at barrier. B. The wave has a wavelength of 36 cm and a speed of 1.2 m/s. Calculate the frequency of the wave. V equals f lambda in any form, or f equals v/lambda. Or f equals 1.2/0.36. F equals 3.3 Hz. C. Complete the following sentences. An echo is the name for a reflected sound or ultrasound. Wave. The waves that form an echo are a type of longitudinal wave. Longitudinal waves are made up of compressions and rarefactions. 6. A. Fig 6.1 shows an arrangement of glass prisms inside a box. The angles of the prisms are 45 degrees, 45 degrees, and 90 degrees. This is a device used to view objects that are behind a wall. The incident ray of light undergoes total internal reflection in the prisms. On Fig 6.1, complete the path of the ray through the device and show the ray as it emerges from the box. Incident ray travels straight on at first face of prism 1. Ray reflected through 90 degrees at sloping face of prism 1 continues vertically downwards to sloping face of prism 2. Ray reflected through 90 degrees at sloping face and leaves box horizontally. B. Show that the refractive index of glass with a critical angle of 45 degrees is 1.41. N equals 1/sin C in any form, or N equals 1/sin C. N equals 1/sin 45 or N equals 1/0.707 and N equals 1.41. 0625_S20_MS_43.pdf 6. A. Fig 6.1 shows crests of a sound wave after reflection from a solid surface. On Fig 6.1, draw 3 crests of the incident wave. 3 wave fronts parallel to each other. 2 wavelengths same as reflected by I. 3 wave fronts at same angle to barrier as original. B. Tick 4 statements in the list below that are false for a sound wave that is audible to a healthy human ear. Second, third, fifth, and sixth boxes ticked. C. State a typical value for the speed of a sound wave in water. 1500 m/s. 7 Fig 7.1 shows red light traveling from air into a prism made of diamond. The path of the red light is incomplete. A. The refractive index of diamond is 2.42. Calculate angle x. Sin I/sin r equals n in any form. R equals 18 degrees. B. Explain the term total internal reflection. Light traveling from optically dense medium to optically less dense medium. All light reflected or no light refracted. Angle of incidence is greater than the critical angle. C. The angle y is greater than the critical angle of diamond. On Fig 7.1, draw the path of the red light through and out of the prism after point A. Ray reflected at face AB with I equals R by I. Ray refracted at face BC and bent away from the normal. 0625_S21_MS_41.pdf 6 Fig 6.1 is a full-scale diagram that represents a sound wave traveling in air. A. On Fig 6.1, mark 2 points, each at the center of a different compression. Label both of the points C. 2 points labeled C at the center of the 2 compressions. B. The speed of sound in air is 330 m/s. Measure the diagram and determine the frequency of the sound. 6200-6500 Hz or Lambda equals value from 0.051 to 0.053 m seen anywhere. F equals v slash lambda in any form or 330 slash 0.052 or 330 slash 5.2 or 63 ms. C. The wave reaches a barrier. Fig 6.2 shows the wave passing through a gap in the barrier. The frequency of the wave is increased to a value many times greater than the value obtained. In B. Describe and explain two ways in which a diagram representing the wave with the greater frequency differs from Fig 6.2. Compression/rarefactions closer or more compression/rarefactions in same distance. Less diffraction/spreading out because of smaller wavelength or ratio wavelength/gap width smaller. 0625_S21_MS_42.pdf. 6. A. Fig 6.1 shows a ray of green light passing through a prism. A ray of blue light is directed towards the prism on the same path as the ray of green light. On Fig 6.1, draw the path of the blue light through and out of the prism. Blue ray refracted more towards normal at first surface. Refraction away from normal at second surface. Ray of blue light below ray of green light and diverging throughout path after entering prism. B. The wavelength of the blue light in air is 4.8 times 10 to 7 m. Calculate the frequency of the blue light. V equals F lambda in any form or F equals V slash lambda. F equals 3 times 108 divided by 4.8 times 10 to 7. F equals 6.3 times 1014 Hz. 0625_S21_MS_43.pdf. 5. A. Fig 5.1 shows a wave on the sea approaching a harbor. I. On Fig 5.1, draw three wave crests in the harbor. Part of a circle, at least quarter of a circle, centered on center of gap. Wave same wavelength as incident waves. 2. Another harbor has a much wider gap between its walls. Describe and explain how the pattern of wave crests in this harbor is different from the pattern you have drawn in I. Waves pass through gap remaining straight. Less/no diffraction occurs. B. A sound wave of frequency 850 Hz travels through sea water. The speed of sound in sea water is 1500 m/s. Calculate the wavelength of this sound wave in sea water. 1.8 m. Lambda equals V/F or 1500/850 in any form. 6. Fig 6.1 is a full-scale diagram of a lens and an object O. A. The focal length of the lens is 3.5 cm. On Fig 6.1, mark and label with the letter F the positions of the two principal focuses. Principal focuses marked in correct position. B. On Fig 6.1, draw three rays to locate the image. Draw an arrow to represent the image and label the image I. 1 mark for each of 1 correct ray, 2nd correct ray, 3rd correct ray and image, labeled I, in correct position with arrow at bottom. C. State three properties of the image I. Real, inverted and enlarged. D. A student incorrectly states that this lens is being used as a magnifying glass. I. State how the image produced by a magnifying glass is different from the image I. Image produced by a magnifying glass is upright, not inverted or virtual. 2. The student moves the object O to a position P so that the lens shown in Fig 6.1 acts as a magnifying glass. On Fig 6.1, mark a possible position for P. Position marked between principal focus and lens. 0625_S22_MS_41.pdf. 7. Fig 7.1 is a full-scale diagram of a small nail N in front of a thin converging lens. The line L represents the lens. The focal length of the lens is 3.0 centimeters. A. Rays of light, parallel to XY, are traveling towards the lens. Describe what happens to the light after it passes through the lens. All the light meets at a point or is focused or intersects. All the light travels towards a point. It then diverges or spreads out from that point, or point of convergence is on XY/ at F/ the focal point / principal focus / 3.0 cm from lens. B. On Fig 7.1, mark and label with an F each of the two principal focuses of the lens. Two marked points on XY 3.0 cm from center of lens, and one on left and one on right, and each labeled F. C. The small nail N, of height 1.2 cm, is positioned 2.0 cm to the left of the lens. I. By drawing on Fig 7.1, find the position of the image I of N and add image I to the diagram. Two of these rays from tip of N drawn. Ray that seems to come from left-hand principal focus and emerges from lens paraxially. Paraxial ray to lens and then towards right-hand principal focus. Ray towards / through center of lens. Two rays traced back to intersection and line from intersection to axis and line labeled I. 2. State and explain whether I is a real or a virtual image. Virtual and light / rays do not pass through I, or virtual and light / rays only seem to come from I, or virtual and produced by diverging rays. Virtual and real rays do not meet. 3. State the name given to a lens when it is used in this way. Magnifying glass. 0625_S22_MS_42.pdf. 5 sound waves are longitudinal and electromagnetic waves are transverse. A sound wave used for a medical examination has a frequency of 1.5 MHz. I. State and explain what type of sound wave this is. Ultrasound or sound frequency above audible range. Frequency 20 kHz or 20,000 Hz. 2. The wave travels through soft human tissue at a speed of 1.3 km/s. Calculate the wavelength of the wave in soft human tissue. 8.7. 10 to 4 m or equals V/F or V equals F in any form. Equals 1.3. 103/1.5. 106 or 8.7. 10 n. B. Describe one use of X-rays in medicine. Basic description of use, e.g. X-rays for detecting broken bones. Additional detail, e.g. X-rays pass through soft tissue and not through bone. 6 Fig 6.1 is a full-size ray diagram showing the formation of an image by a thin glass lens. A. Determine the focal length of the lens. 1.9. 2.1 cm. B. Circle 3 items in the list which describe the nature of formed. Enlarged, same size, diminished, inverted. Upright, real, virtual. Circle round enlarged. Circle round inverted. Circle round real. C. State one feature of a virtual image. Not an intersection of rays or cannot be formed on a screen or cannot be projected on a screen, or light rays do not pass through image, or light rays do not meet, or light rays do not converge. 0625_S22_MS_43.pdf. 6. A. I. Fig 6.1 shows crests of a plane water wave approaching a barrier with a gap. On Fig